So in the last video of today's topic or this week's topic is the modification of the Gaussian plume equation. So how would we adjust this to really reflect real world conditions? So there are a lot of limitations that this model cannot really deal with. For example, terrain. Terrain means like how your geography or your elevations are changing. For example, you have a mountain, you have a valley, you have a small part that comes up and then goes back down. So complex presence of hills, valleys, other topographical features can significantly affect pollutant dispersion. So we need to adjust the model for the Gaussian plume to necessarily account for these variations, often using empirical data or more complex modeling techniques. Now, again, the other thing is the class stabilities. You remember the A to F, the atmospheric stabilities ranging from very unstable A to very stable F, and this impacts the dispersion completely. So it affects them through sigma Y and sigma Z. We have the Pascal-Clifford curves, which are the ones we use to get sigma Y and sigma Z based on the stability. Now, remember the delta H that we talked about earlier, that actually the plume starts not right after the stack, but way above the stack after a small delta H. So the effective stack height H is influenced by the plume rise, which actually depends on stack velocity, stack diameter, temperature. So we need to take this into consideration to calculate the delta H. And we use something called the Briggs equation to estimate the plume rise. There is also something called building downwash. So, for example, if you have a tall building next to your stack, what happens that the plume starts and then it finds a building and then it starts to disperse around the building. And this is what we call building downwash. So there will be a lot of pollutant that just goes down just because of building just right close by. And we also have to take this into consideration when we are looking for models. So the modification of the Gaussian plume equation, the very first thing or the very important thing is to have something what we call a mirror. So basically when, let me just get the pen again. Sorry, not sure what happened. Okay, so if this is my stack and then the plume goes like this, and here is your ground, theoretically, the model assumes that the plume keeps dispersing this way. While this really doesn't happen like this. Actually, what happens is that part of this plume is reflected off the ground and goes this way. So now we have to add another term in the equation to account for this mirroring effect. And doing this, we add part here where we are talking about how this is affecting the mirroring. So we can use this more general equation rather than the one that we have before. So at large Z, the equation becomes the same as before. Why? Because Z will be much, much more than H. So when you count these two together, they will be the same as the equation that we had earlier. So if at large Z, so you can actually forget about the H. So you can just add these two together and then the equation becomes the one that we had before. Also for conditions of Y equals to 0 and Z equals to 0, which is the line on the ground directly. So this basically writes this one on the ground right after it. We can also calculate the C. It will be much easier. And we can get also this equation, which is Cu over Q, 1 over pi sigma Y sigma Z times e to the power negative 0.5 h over sigma Z square. And this equation we use usually to describe the line on the ground just before the plume. So for example, here, compute this value for stability C at a distance of X equals 2.5 kilometers and H equals 50 meters. So we can calculate it. And then at different X's, we can calculate it. You can see that at different heights, we have this curve over here, where this is CU over Q. This is here your X. And here there are different H's. And based on the X, we can and the H, we can calculate different CU over Q. So this gives us directly the concentration right at the line just in front of it. The plume rise, which is the delta H, that's how much it goes above the physical stack. And the factors that we talked about earlier that affects it are the stack velocity, the stack temperature, stack diameter, and ambient wind speed. And we can use this equation. Delta H is equal to Vs, where Vs is the stack exit velocity, D, diameter, over U, which is the wind speed, times 1.5 plus 2.68 times 10 to the power negative 3, P, which is the pressure in millibars, and please make sure you can follow the units, times D, which again is the stack diameter, Ts minus Ta, and Ts is the stack gas temperature, Ta is the atmospheric temperature, over Ts, and they are all temperatures are in Kelvin. So looking at this example, estimate the plume rise for a 3-meter diameter stack whose gas has a velocity of 20 meters per second when the wind velocity is 2 meters per second, the pressure is 1 atmosphere, and the stack and surrounding temperatures are 115 respectively. So we just directly substitute in the equation. So delta H is equal to 20 times 3 over 2 times 1.5 plus 2.68 times 10 to the power negative 3 times 1013 times 3, and then we convert this into Kelvin, 373 minus 288 over 373. This gives you a 101 meter, and that's only delta H. So the effective stack height H is equal to H plus delta H. So with this, we conclude the chapter. So the key takeaways is you need to know what's the importance of accurate modeling in air pollution control, and what are the different models for different scenarios. And there is a need for continuous improvement adaptation for models. Every year in the spring, there is a modeling conference that happens in Raleigh, North Carolina. That's actually where the EPA air pollution group sits. And this is a modeling conference getting modelers from all over the world that actually discuss how to improve the model to accurately describe things, and they come with recommendations, and that's when they do new modifications for the model every year. Thank you for watching, and we'll gear to the next topic, which will be control equipment.